Bismillahirrahmanirrahim. Alright class, Assalamu alaikum and welcome to the third lecture of week 6, where we are going to elaborate a little further on the field of an infinite uniform sheet of charges. In the last class we had derived an expression for an infinite sheet which is characterized by its surface charge density, and this sheet was infinite, and we decided to put that sheet on an x equals to 0 plane. So we at the end we got an expression for electric field intensity due to this whole infinite sheet, which was put on x equals to 0 plane, and we discovered that the field on positive x-axis, field on any point on this positive z-axis is going to be defined by this expression. And we noticed that in the magnitude portion of this field, that is this, there is no x, y or z. It means that magnitude of the electric field intensity due to an infinite sheet does not depend on the position. The magnitude does not depend on position, meaning that it does not matter how far you are with respect to this sheet, your field points, meaning the eyes, are going to experience the same amount of field. Okay, so it does not matter whether you are 1 millimeter away of this sheet of charges, or if you are 1 million or 1 billion miles away of this sheet of charges, you are going to experience exactly same amount of field. All right, so the direction of the field was the vector which was perpendicular to which was perpendicular on the plane on which this sheet was placed. So if sheet was placed on x equals to 0 in particular, or in general x equals to constant plane, so the direction of the field will always be perpendicular to that plane over which the sheet was placed. So if you see the sheet from the top, you're going to experience this sort of arrangement of charges, where this is the sheet. I have shown some thickness to it, but you should always remember that there is no thickness in this sheet of charges. And secondly, this sheet of charges is made up of entirely charges. There is no concept of any material present over here. So only we are interested only the charges, not on the material. We are not interested in the material on which the charges are present. The charges may be arranged in a form of a sheet in free space. It can be arranged on a metal surface. The material of the surface is not important. The material is not important at all. The only thing which is important is the charges. All right, so this is the sheet of charges. All right, and we had taken the field point to be here, and we said that since we considered that this is a positive charge, we said that the field will be at this point will be in the direction of AX. Okay, according to that formula, and we derived that formula yesterday, I mean in the last class. Okay, so since the magnitude has not x, y, z in it, so it does not matter whether the point is here or the point is here or the point is here, I mean field point, or the field point is here or the field point is here or the field point is here or the field point is here. It does not matter wherever the field point may be, the amount of field experienced by the field point due to this infinite sheet of charge would be the same, because it does not matter whether you're here, if you're looking the sheet from this point, the amount of sheet, the area of this sheet towards the right of this point is infinity, and towards the left is infinity, and above infinity and below infinity. Whether you are standing at this point, the area of the sheet towards the right of this point is infinity, towards the left is infinity. So it does not matter whether you observe this sheet from here or here or here or here, or a million miles on the right or a billion miles on the left, you will experience the same amount of sheet everywhere. Okay, as long as the sheet is of uniform surface charge density, meaning that rho s has got a constant value. Yeah, so it does not matter where you are standing, you are going to experience the same amount of magnitude of field. All right, so the direction of field means we should always remember that what is this physical significance of the direction of field? What do we mean by what do we mean physically by direction of field? Is that if we put a positive Coulomb test charge, or positive 1 Coulomb test charge over here, in which direction would it move? So if it is made up of plus charges, so definitely it will move away of the source. And if this sheet is made up of negative charges, if you put the judge charge, which is of plus 1 coulombs, if you put a judge point charge here, it will definitely move towards the sheet. So if had this sheet been made up of negative charges, the formula here would only have a minus sign. Okay, let me write it in blue. If rho s was negative, okay, so the formula for electric field intensity at any point below the sheet will have the same magnitude, but this time, since this negative charge will attract the positive judge charge, the only change will be in the direction of the field. Okay. All right, and in case of for example positively charged sheet, if the sheet was positively charged and we had taken the field point anywhere here above the sheet, obviously it will push the judge charge away if the sheet is positively charged. In that case, what is this direction? This direction is minus ax. This direction is minus ax. So now if we had gone above the sheet, meaning on towards if we had taken the field point on the values where x at the points where the x has got negative values, so in that case the formula for ex would remain same because the magnitude is the same. The only difference is going to be that if you take your field points here and if the sheet is positively charged, the direction of the field will be opposite now. And had we taken a negatively charged sheet over here and field points above this sheet, meaning in the region where the values of x are negative, so definitely this sheet would attract these judge charges. So in this case, the formula for formula for field will have, magnitude the same. So only difference will be in the direction of the field, which would be this time it will be plus ax. So in the case of infinite uniform sheet of charges, the magnitude remains always the same. The only difference happens in the direction of the field, and that direction is decided on the relative position of the field with respect to the source. So this is a very important point to discuss. All right, so if we had a sheet which is on xz plane, if the sheet was like this, placed like this, XZ plane, in that case, obviously, if you had chosen the point, if the field point to be here, and let's say the sheet is positively charged, and if you wanted to find the field here, the magnitude would be the same, rho s upon 2 epsilon naught. The direction would change now. If you put a positive charge, 1 Coulomb charge here, it will push the charge in this direction. So the direction of the field would be positive AY. If you had taken it to be a negatively charged sheet, if rho s had been a negatively charged sheet, so this negatively charged sheet would have attracted the judged charge towards it. So the direction of the field on the right hand side of the sheet would be negative AY. And for a positively charged sheet on XZ plane or Y equals to constant plane, a positively charged sheet on Y equals to constant plane would push a charge, a positive charge away. So a positively charged sheet will push the charge away. So the direction of field would be minus AY on the left hand side of this positively charged sheet. And if this sheet is negatively charged and you wanted to find the field at this point, the direction of that field would be towards right, because a negatively charged sheet would attract a positive 1 Coulomb charge towards it. Okay, notice that we are talking only about the direction of the field, because magnitude of the field is independent of any position. So this is something to be remembered while solving the problems related to infinite sheet of charges. Remember that these are the special cases on which we had put this sheet on x equals to constant plane or y equals to constant plane, but you should always remember that the direction of the field is always perpendicular to or normal to the sheet. So generally we can write it like this. So this is the general formula that we should always remember, we should always keep in our minds. So let's apply the theory of infinite, the theory of the field of infinite uniform sheet of charges to find a practical, not practical, but something. Let's try to apply that on an application which you have already discussed in your pre-engineering, perhaps. You must have studied a device which is known as infinite parallel plate capacitor, in which we have got two metallic sheets of infinite areas and which are very close to each other. The distance is very small, and the sheet areas of the sheet, both the sheets are infinite. So consider that we have got this set of axes, x here, y here, so definitely z is going into the board. Okay, this time I have changed the orientation a little bit, and we have got a positively charged sheet on x equals 0 plane. This is given by rho s plus, this is x equals 0 plane. Okay, and after some very small distance a, we have got another sheet which is negatively charged, and this sheet is placed on x equals to a. All right, so the areas of both the sheets, areas of both the sheets are infinite, and the spacing is very small. All right, the important thing is that the magnitude of rho s plus is equals to rho s minus, as this is true in the case of a parallel plate capacitor, that whatever amount of positive charge you have accumulated on one plate or one pole or one terminal of the capacitor, the same amount of charge is accumulated on the other plate, but with a negative or opposite polarity. Okay, so this sheet has got infinite area, this sheet has got infinite area, this sheet has got the density rho s minus, this sheet has got the density rho s plus. The magnitude is same. This is positively charged, however, and this is negatively charged, however. Okay, so if we had chosen, so you should expect that if it is positively charged, the field due to this positively charged sheet would be normal to sheet and pointing away of the sheet. All right, because pointing away means if you put a judge charge here, it will be pushed away. If you put a judge charge here, it will push the judge charge away. Anywhere, wherever, if you try to put a judge charge here, it will be pushed downward. So these arrows are the direction of the field. Okay, and if you put anywhere in the middle of these two parallel plates, if you put anywhere within this volume any positive judge charge, it will be attracted by this negatively charged sheet. So the positive charge will push the charge upward, and negatively charged sheet will pull that charge towards it. So in essence, the field within these two parallel plates is going to be pushed towards the negatively charged sheet. Okay, and at the bottom, the effect of this positivity at the bottom of this positively charged sheet, the effect of this sheet will be the direction of this sheet will be or the direction of the field due to the sheet will be downwards, and the direction of field due to this sheet will be upwards. Is it upward, downward? And anywhere above this negatively charged sheet, anywhere, if you try to get the direction of the field due to this negatively charged sheet will be towards this sheet. The direction will be towards this sheet, and the direction anywhere above this negatively charged sheet, the direction of the field due to this positively charged sheet, it will be away. Because if you put the field, if you put a positively charged judge charge anywhere above this negatively charged sheet, if you put any charge here, positive charge, it will be attracted by the sheet and pushed away or repelled by the sheet. Similarly, if you put any positively charged judge charge here, judge charge meaning +1 Coulomb charge here, it will be pushed by this positively charged sheet and it will be pulled towards itself by the negatively charged sheet. And the amount of or the magnitude of that push or pull is the same, because the magnitude is independent of the distance with respect to the sheet, which we have already discovered. It means that the field outside the volume, which is covered by these two parallel plates will be zero. इस parallel plate capacitor के बीच के अलावा जितना भी वॉल्यूम है वहां पर फील्ड जीरो हो जाएगी, क्योंकि पॉजिटिवली चार्ज शीट नेगेटिवली चार्ज शीट के इफेक्ट को कैंसिल आउट कर देगा. सो the only field which will be present, that field will be present within these two parallel plates, and that field can be written as field due to the positively charged sheet plus field due to the negatively charged sheet. Okay, so the field due to the positively charged sheet within this volume, field due to this positively charged sheet within this volume will have magnitude rho s plus divided by 2 epsilon naught, and the direction is ax. AX. Okay, and the field due to the negatively charged sheet, that is E minus, within this volume between these two plates has got the magnitude rho s minus divided by 2 epsilon naught, and again the direction of the field is AX. Okay, so I can write that the total electric field is rho s plus upon epsilon naught AX, which is equals to rho s minus divided by epsilon naught AX. So this is true if the sheet is placed on x equals to 0 plane or x equals to a plane. Had we put it on y equals to 0 plane or y equals to a plane, this one on y equals to 0 plane and this one on x equals to y equals to a plane, the only difference would be in the direction of the unit vector. Here we will have a vector which will be perpendicular, a unit vector which will be perpendicular to y equals to constant plane, meaning we would have ay here. Same is the case with if we had put this sheet on z equals 0, this sheet on z equals to a. The only difference would be in the unit vector, and that unit vector must be perpendicular to the sheets. So the idea to discuss this application is to demonstrate why the electric field outside a capacitor is 0, and it is, synergetic or additive within these two parallel plates. The field is synergetic or additive within these two plates, and it is destructive or zero outside these two plates. So this is how we calculate the expression of field within these two parallel plate capacitors. And this is obviously ideal case in which the areas of the sheets are infinite. But if this result can also be used for the cases where the area is sufficiently large as compared to the spacing between the two parallel plates. So this result can be used for practical parallel plate capacitors with very little to no or negligible inaccuracies in the results. So now by now you must have understood implicitly, if not explicitly, that the field has got, the electric field especially, has got, or any vector field effect has got a direction associated with it, and it is really necessary to show that direction, or the overall field there should be some way to depict that, to give some physical sense to that. There should be some way to sketch that magnetic field effect which we are interested, electric field or magnetic field or any vector field effect in which we are interested. So since we are studying electric field, so there should be some way to depict or sketch those fields, those vector fields. So it means that if we are interested in something which is scalar, we don't need to worry about the directions of plotting the magnitude. We can simply give it in the form of a graph, okay, with respect to some distance or some time, what will be the magnitude. So you normally have graph, you have studied several graphs, maybe you must have studied somewhere in your circuit analysis sinusoidal graphs, and in signal systems different graphs are there. Those representations with respect to time or any dimension or space is nothing but the sketch of a scalar entity. How about vector entity? So sketching a vector entity, since we are discussing electric field, we will focus to electric fields only. the topic which we discussed prior to this discussion was the parallel plate capacitor, field of a parallel plate capacitor, and we were trying to figure out the direction of the field above and below, above positively charged and negatively charged. And so what is in essence the direction, or how should we define or sketch the direction of an electric field, or the magnitude of electric field simultaneously with the direction itself. So this topic is a very supplemental and small topic, but it's really important and fundamental to understand that the direction of electric field intensity and the magnitude simultaneously can be sketched on a page or a paper or a board or a computer screen in the form of the streamlines, which are nothing but sketches of the field. And the streamlines are nothing but the direction of the field. Direction of the field is nothing but the direction in which a positively charged 1 Coulomb judged charge will move. This is the direction of the field. That's it. Okay, so there are several ways to it. Let's say we have got a positively charged point charge and we want to find the field surrounding it, okay, the direction of the field, or we want to sketch the field surrounding it such that we get not only the direction of the field but also some sense of magnitude. So there are several ways to do it. So the most raw way would be to say that, okay, if the field point is close to the point or to the source point, if the field point is close to the source point, then the field will be larger, and if it is away, then the field will be smaller. Okay, but the direction of the field will be along the line joining the field point and the source point. So this is a way to express it. If the field point is again closer, so the field will be along the line joining the field point and the source point, but since it is closer, then the field will be larger. So the length of the arrow is showing the magnitude. So the magnitude of the field is directly proportional to the length of the arrow, and the arrowhead is showing the direction. So in such case, such sketch, what we are getting is both the direction of the field at each point and also the magnitude by seeing or measuring the length of the arrows. But this is not very intuitive way to do it, so let me call it sketch or scheme number 1, or streamlines scheme number A. So this is not very intuitive. So we are taking randomly different points and trying to sketch the field. So it is not intuitive. To make it intuitive, another approach can be this approach B, which is actually showing symmetrically the field in all directions. This looks more intuitive. Okay, if we have got a point charge here, so the lines which are closer to point charge are longer, the ones which are farther are smaller. So wherever you see a sketch of the field where no point charges are shown, where no sources are shown, if you have some complex arrangement of charges, a complex arrangement of sources in which those sources are not shown but the field formed by those sources are shown. So if this scheme is used, you can see that wherever you will have longer lines, the magnitude of the field is higher in that area, and wherever the length of the arrows are shorter, so the magnitude of the field is smaller. But this scheme will give you, if there is a complex charge arrangement, using this scheme will mess up with the diagram, and it will not be very understandable. It will not appeal to your intuition, or your it will not give you directly the idea of the field where the field is very high or where the field is small. So another way. Why? Because there are different lengths, so maybe you can mix up. Okay, I've shown only 3 lengths. Maybe the field in a very complex arrangement can have 20 different lengths, so it will not be very intuitive to see the sketch and figure out that which area has got higher field and which area has got smaller or a smaller field. So there is another scheme for that. We'll call it scheme 3C, in which the length of the arrows are kept constant, but the thickness of the arrows are more thicker near the source, to show that the magnitude of the field is higher near the source, and as you move away the thickness is reducing but the length is always there. This scheme looks nice because you don't have to worry about the length of the arrow. This time you have to worry about the thickness of the arrow. But how about if we have got a complex charge arrangement? How many thicknesses can you introduce? So this arrangement will not give you a intuitive or an appealing picture of the field sketch if the charge or the source arrangement is complex. So a relatively simple and widely used scheme of showing the direction of the field is this one. Simple arrows. Positive charge, simple arrows. Anywhere if you try to put a judge charge, it will be pushed away. Had it been a negative charge, the direction of the arrows would be reversed. Okay, so we are just taking the example of positive charge. But if you see it closely, there is also a sense. Right now you can see that there is only the sense of direction. There is no sense of magnitude of the field, because here we had used thicker arrows near the source, here we had used longer arrows. So in scheme B and scheme C there was some sense of magnitude associated with these arrangements, but here the arrows are of same length. And it means that scheme D is only providing the direction of the field, not the magnitude of the field. But there is that's true. But if you see that as we are going away of the source, the distance between the arrows is getting larger. Okay, so indirectly this scheme not only gives the direction of the field, but it is also giving the magnitude of the field, that as you go away, as the field weakens, you will see lesser number of lines as compared to the place where the field is stronger. In that case you will see more number of lines jam packed in a smaller area. So you will directly realize that okay, this area in which there are several lines of the field, that area contains higher magnitude of the field, and the direction of the field is given by the arrow. So this scheme is the widely used and simplest and most illustrative scheme which is used to sketch the field, and we call all these arrangements as streamlines, and streamlines is nothing but the direction of the field. So this is streamlines of 1 point charge. So plus positively charged point charge, okay, a positive point charge. So let's say we have got a field like this which is flowing in this direction. So definitely this is an arbitrary field which I have plotted. So these are the streamlines, these are the generic direction of the fields. But if I want to find at any one point the direction of the field, what that direction would be, take the judge charge, put it here and leave and see where it goes. It will go wherever it will go, that direction will be the direction of electric field at this given point P. Okay, so we can call it probably EP, is it? So the direction of the field will always be tangential. Direction of the field at any point will always be tangential to these curves, these streamlines, if you like to call it, tangential to these streamlines at the point at which you want to find the direction of the field. That's simple. Okay. So always remember that the concept of the streamlines or sketches of the field is limited to 2 dimensions only. So you don't have to worry about too much about the visualization, because this concept is limited only to 2 dimensions. In 3 dimensions we have got other ways to represent or sketch the field which is out of scope of our subject. So let's say we have got a 2-dimensional field x and y. Okay, this is the field and we want to find, this is the direction of the field. I'm just making it arbitrary. So if I want to find the field at this point, so if take the positive charge, put it here, where will it go? It will be tangential to this curve at this given point. So this is the direction, this will be the electric field intensity at this given point. Okay, so if I resolve this field into its x component and y component, so here we have got the x component of the field Ex and the y component of the field, I'm just writing the scalar components. All right, so if I take if I measure this height, and let's say this height is delta y, so and this width is delta x. So trigonometry tells us that the ratio of Ey upon Ex is delta y upon delta x. And if I double this delta x, so this delta y will be proportionally increased. If I make it half, so the delta y will also be proportionally decrease, so the ratio will always be the same. If I make this delta x so small that this delta x, this incremental x becomes differential x, so this incremental y will be proportionally decrease and it will become delta, it will become dy. If delta y will become dy, if I make this delta x to become differential, this incremental y will also become differential. So what we can write is Ey upon Ex is equals to dy upon dx. Okay, from geometry we got this expression, and this is the fundamental expression for the streamlines. And let's take an example that, let's say in rectangular coordinates we are given with a field plus y on x square plus y square ay, and if I want to find the streamline, the equation of a streamline, SL is not a standard short form, just I am writing for the sake of time. So equation of a streamline at point P, and I am just taking an arbitrary point 1, 2, 3. So how to proceed, how to find this equation of the streamline of this electric field at this point? We have to use this formula. Take the y component of the field, which is this y upon x square plus y square, and divide this by x component, which is x upon x square plus y square, all right, and that should be equals to dy upon dx. So dividing is equals to multiplying by reciprocal, so what you'll get is y upon x equals to dy upon dx. So if you cross multiply, what you'll get dx upon x is equals to dy upon y. To find the equation, solve it, integrate both sides. Okay, so on the left hand side what we'll have 1 upon x dx, on the right hand side we have got 1 upon y dy. So on the left hand side we will get ln x plus some constant is equals to ln y plus another constant. So we are combining two constants and making that constant as one constant c. Okay, so let's make combine the two constants and make them constant c1. Okay, so in order to aid with this expression, if I could just, you know, make it like this, ln x is equals to ln y is equals plus ln x is equals to ln y plus ln of c, ln of c, where ln of c is c1. तो इंटीग्रेशन में कांस्टेंट्स के साथ हम खेल सकते हैं, it does not matter. Okay, so ln x is equals to ln y multiplied by c, is it? Using the property of log x plus log y is equals to log xy. So taking antilog on both sides, what we'll have x is equals to cy. Okay, so this is an expression for this particular example. It's not general derivation. I'm just trying to show you how to use it. Okay, so if you want to find out the field at this point, just replace, you have to find c. To find the c is nothing but x upon y. X is 1, y is 2. So the final expression for the streamlines of this field at this point will be x is equals to 1 upon 2 y, or y is equals to 2x. This is the answer. Okay, so this was the last section of the last topic of chapter number 2, and we have completed the electric field intensity, or the force field category of vector effects for static charges. Okay, refer to that table which I talked about earlier, which I gave you at the end of the 4th week lecture, the 3rd lecture of week 4. I gave you 2 tables, one for electrostatics, one for magnetostatics. Now this chapter, by the end of this chapter, we now know how to calculate the electrostatic field intensity of 4 possible charge distribution: 0-dimensional charge distribution, 1-dimensional charge distribution, 2-dimensional charge distribution, and 3-dimensional charge distribution. And after that we have covered the supplementary topic of streamlines. In the next chapter we are going to take the second vector field effects, which belongs to the flux density kind of vector field effects for the electrostatic charge distributions. All right, till then, good luck, and Study hard, buckle up, because we are going to speed up things very fast. So I would hope that by the end of uh, after 5 days from now, from listening this lecture, after 5 days from listening this lecture, you would have completed all the problems of chapter number 2, at least the odd ones, and the drill problems of chapter number 2, and you have also gone through the solved examples. Assalamu alaikum.